Attention is order n squared. That's true, and it's taken to mean attention dominates a transformer's cost. For most context lengths people actually used, it didn't. Look at the real matrices: query, key, value, output, 4D by D multiplications, 8 ND squared flops, counting a multiply add as 2. The feed forward block adds 16 ND squared more. Total 24 ND squared. Linear in the tokens. Now the scores. Query against key, n tokens by n tokens, once per head, summed to 2n squared d. The value weighted sum costs the same again, 4n squared d, the quadratic term. Set them equal, 24nd squared, 4n squared d. The d's cancel to 1, leaving n equals 6d. Below that width, linear wins. Above it, the square does. GPT-3, width 12,288. Crossover at 73,156 tokens. Real shapes and softmax included. It shipped with context 2,048. Attention was 2.7% of the layer. Meta's Llama 3 2024, width 4,096, crossover at 26,418 tokens. It launched with context 8,192. Attention was 24%, still the minority. Months later, Llama 3.1 stretched the same architecture to a context of 131,000 tokens. Same crossover. Now attention is 83%. The line got crossed. Here's the honest part. The n by n score matrix in memory only cares about n squared, not d. It matches the feed-forward layer's own memory at 448 tokens, 59 times sooner than the flop crossover. That's why flash attention matters. It barely changes the flop count, it just stops writing that matrix to slow memory, tiling the math instead. 3 times faster on GPT-2 at sequence length 1000. An input-output story, not a flop story. So don't call attention cheap. It's expensive in memory almost immediately, which is why flash attention exists. Past 100,000 tokens now, it's expensive in flops too. Attention really is order n squared. What was wrong was assuming that made it expensive right away.